All right, welcome back. Mr. Martin here. We are in a brand new unit, 8.1. We're going to talk about functions and domain. We're going to determine what makes a function. There's a lot to it, so there's a good chunk of stuff that you got to read and start putting down to memory. But we're going to describe those elements of domain and range, and then we're going to work through with domain and range. Alright, so first thing that we need to know, a function, this is what we call a correspondence or a relationship between two sets. We're talking x's and y's. We've used them before. Okay, and this is where each element of x is matched to one and only one element of y. Okay, and as we dive deeper in our things to know, you're going to understand this a little bit better. But we call our set of x values, this is what we call our domain. So just always think domain x, okay? Commit that to memory. The x values are our domain of our function. And they're also known as our input values, okay? So remember, like if we have this machine, we're plugging something in and spitting something out, okay? So the set of x values is the domain, okay? And then the values in y that those domain values get mapped to, these are what we call the range or the output. Okay, and what actually makes a function in terms of x and y, this is hugely important. Each x value can only have one y value. Okay, having the same y value for multiple x values is certainly okay, but if you have the same x value, it cannot have two different y values. And you can see as we plug along. So I got a lot of different little graphics for you that I think will be helpful. Okay, this first one is identifying like our input, the relationship, and how the output works. So if we're talking about multiplying by 2, these three sections here in this table, if you take a look, let's say we input a 0, and then we got 0 times 2, and then now we have an output. Put in a 1 times 2, etc. So this lets us understand that type of relationship in our function, our input, and our output. Okay. The next piece that I got is a graphic of what an actual function looks like. Remember, we can have any kind of function name. This part of our function notation, which we have talked about in previous lessons, this is what our input is, and then on the opposite end of this equal sign, outside of that parentheses, this is what our output is going to be. Okay, so if we have an input, this is what our output is, and we would read this off as f of x equals x squared. Alright, here if we are looking at this example, it says this tree grows 20 centimeters every year. And this is saying that the height of the tree is related to its age using our function h. So they've named this function h, and they're saying, hey, if we have an input of age, right, okay, because this is the independent variable. Remember, x values are independent. If you want to write that in, x is independent, and then our y values are dependent. Remember, the y's depend on the x. Okay, and age, right? Time doesn't depend on anything. It just keeps on going. So this is very important for you to recall from our previous sections. Just remember that the x's are independent and that the y depends on the x value. So this is a good little example to look at as well. Okay. Remember, if and anytime this is going too fast, remember, rewind the video, watch it several times until you completely understand what I am talking about. I like this graphic here because it just reminds you that x is just a placeholder. So if we got this function here, f of x equals 1 minus x plus x squared, if we have a different input rather than x, like right now x is our input, so that's what we see here, and this is our function. But if we were to input a q, all we're going to be doing is replacing all of those x values with a q. So you can see here 1 minus q plus q squared. Same with this capital A, and same with this symbol here, which is theta. And you're going to learn about that more in geometry, use it in trig or pre-calc, whatever other math class you go to. Same thing here. If we're using an input of 2, we're just going to simply replace all of those x values with a 2. So this is very important to know when we work with function notation. We're going to be doing this a lot in this unit. So make sure you get a hold on that. And we have what we call a set. This is just a nice little description that, you know, a set can be any type of collections of things. It doesn't have to be numbers. It can be a certain set of numbers, even numbers, multiples of 3, etc. It can be a set of clothes, hat, shirt, pants, shoes, watch, whatever you want. Okay, so just remember, this is what we call a set. And when we describe our sets, as you can see here, we're going to be using these little squiggly brackets. We are back to that set notation that we had done you know, several sections ago. All right, and then this is what we use for mapping. So this here's a definition of a function. Remember, x can only have one y. We can only have that one output for that one input. But when we do this domain and range function mapping here, you know, typically the x is on the left and then the y is on the right. So just kind of get used to that pattern there. The left side will be x, the right side will be y. So like I said, x and y, this is important. So this is a nice little chart to remind yourself of what makes a function and what makes something not a function. So here on the left, remember, an input can only have one output. So if we have this input here, this input cannot have two different outputs. Okay, but we can have two different inputs that have the same output. So I'm going to use this example here. I got my two buddies, Tom and Mike. All right, let's do Tom and Jerry, maybe. Yeah, you know those guys. Let's do Tom and Jerry. All right. So Tom was born on February 12th, 1950. And Jerry was also born on February 12th, 1950. Is that perfectly okay? Yeah, we can have more than one person with the same birthday. I mean, there's only so many birthdays to go around, right? But what we cannot do, right? Tom cannot be born on what is that? May 5th, 1951, right? Tom can only have one birthday. Okay, now more than one person can have the same birthday, but one person cannot have the same birthday. Okay, so this is a good example of a function and not a function, and we're going to do a couple of those here shortly. All right, so our first example number 1, we want to ask ourselves, are the following correspondences functions? And if they are or not in this case, we still want to identify the domain and the range. So remember, an input x can only have one output. So let's take a look. We got our ordered pairs. This is x and y. If you want to label them, you can. So here we got 1's got an output of 4. That's good. 3 with an output of 8. That's good. -2, output of 6. 9, 7, and 4 and 8. So it doesn't look like we have any x value with two different y values, because all of these x values are different. So would this be a function? Yes, I would say so. Okay, and then like I said before, remember when we talk about our domain, we want to use our squiggly brackets and we want to list all of our x values, because remember the domain is our x values. It's always nice if we put them in order. So let's go low to high. So -2 is our lowest. Then we got the 1, the 3, the 4, and the 9. Okay, and then we're going to do the same thing with the range, but here's one little important thing, and I'm going to have you take note of this down below. But when you have multiple values, right? Remember, we can have multiple values in our our set y, right? Because those are our outputs. We only have to write them once, so we wouldn't want to write 8 twice in our range. So let's go ahead and do our squiggly. It's probably not the best squiggly. There we go. And we'll go low to high. So we got 4, 6, 7, and then 8. 4, 6, 7, and then 8. And then what I'm talking about is we had 2 8s. We don't want to write another 8 there. We're just going to keep it at 1. So this is good to go. We are checked off. All right, let's try The second one, we got a table here. We got an x and f of x. Remember, f of x is just the same thing as y. So here, 4 is going to -3, 5 is going to -2, 6 to -1, and then now 4 is going to -4. Uh-oh, we said earlier that 4 was -3. How can it be -4? Okay, remember, this is like Tom having 2 birthdays. So this we cannot do. Is this a function? No, it is not. So no. No, no, no. Well, let's go ahead and list the domain. Our domain would be 4, 5, 6, 7, 4, 5, 6, 7, squiggly. And then our range would be -1, 2, -3, -4, -7. So we got -1, -2. Oops. Should we go on the other way? Those are negative numbers. -7, -4, -3, -2, and -1. Very good. All right. And then now we got, remember, these are x, these are y, these are our domain map circles. Okay, so here we just kind of want to chart the path. All right, well, we got 0 going to 7. That's okay. 1 is going to 2. Uh-oh, it is also going to 4. So is this a function? No, it is not. Right? 1 has 2 different values. All right, now this one's going to be a little different. Okay, so pay attention here. What is our domain? Well, we got arrows or lines coming out at each one of these numbers. So these are all part of a set right here. 0, 1, 3, and 9. Okay, but here on the right, on the y column, right, or the y oval, only 3 of these numbers are being used. This 0 is not part of anything. It's just a number that's put in there. So we got to make sure that we don't include that in our range. So our range only consists of these 3 numbers here. So we just put 2, 4, and 7. Just like that. Really simple. All right. This next one is this function. 1 goes to 4, 5 goes to 4. Hey, that's like Tom and Jerry. They're sharing the same birthday. Is this a function? Sure is. We're going to write that big old yes. Our domain, we got 2 values. That is 1 and 5. And then our range is 4. That's it. All right. So what I want you guys to think about, I got this little note here for you. Okay, a way that you can easily identify if something is a function, or actually identify if something is not a function, is if you look for duplicate x values. If you see an x value and there's 2 of them, like here, 4 and 4, immediately, hey, 2 of the same x value, no go, not a function. Duplicate y values is okay, and then remember that note, you only need to list each value once, okay? And they don't have to be numerical examples only. I got this little list right here. I want you guys to pause the video and see if you can really understand what is making a function. You know, these relationships, is there an input that only has one output? And this is simply a yes or no. You don't really got to go ahead and justify in here. Just justify in your head, think about it. So let's go ahead and pause the video right now and then come on back. Alright, welcome back. So I went ahead and just put some Y's and N's here. And I'm not going to talk about all of these. There's a lot of them on here. But if you look at the first few, like the assignment of the members of a football team to a jersey number, would that be a function? Well, each person only gets one number, right? Like my favorite, Aaron Rodgers, you know, he's just number 12. He's not number 12 and 28. So that member, okay, only gets one jersey number. Okay, what about citizens to social security numbers, right? Each person only gets one social. You're not walking around with 5 social security numbers. Okay, what about students to locker numbers? Okay, you know, we're not going to have 5 kids sharing the same locker number. Okay, so let me do one of the no's. What about zip codes to residences? Well, the reason this is not a function, right? You're going to have however many people living in the same zip code. So it's not like a zip code for each person. Okay, so this is some of the kind of stuff that you want to think about as you are trying to identify if something is not a function or if it indeed is a function. All right, very good. So let's go ahead and move on to example number 2. Okay, and I want you to take note of this note down here first. This is hugely important. This is a good way for you to remember exactly what you're supposed to do with these functions. So remember, it says the value in parentheses. So like here, if you see something in the parentheses, like you just, hey, I don't know what to do with this, and you got this equal sign, well, I'm asking you to look at the function f, which is what we got here. On the right, we got a function h. I am saying, hey, for every value of x, or every input value, every value of x, I want you to plug a 4 into there. And that's going to tell me what our function is equal to. So we're simply going to do that here. So we're going to say f of 4, okay, is equal to 2, but then instead of that x, we're just going to plug that 4 in, and we got plus 9. And then now we just evaluate this right side. So we got 4 times 2, 8, plus 9, 17. Boom. So f of 4, when x is 4, y is equal to 17. So simple. All right. The other part, when you see the value outside, you want to substitute for y. So, I mean, it's kind of leading you there anyways because it's telling you to solve for x. So if you're solving for x, that means we must know what y is equal to. So we're going to plug in a 13 instead of a f of x, and this is our function right here. So we're going to do a 13 instead of that f of x. But we still got the rest of this function, so now we got to do a little bit of solving. Here we kind of just evaluated. Here we got to go back to our solving equation skills. So remember, we want this term by itself. We got to get rid of that plus 9, minus 9, minus 9. 13 minus 9 is going to be 4 is equal to 2x. And then we got to divide both sides by 2, and we get 2 is equal to x. Boom. So when y is equal to 13, x is equal to 2. Alright, so you got the example on the right. I want you to pause the video right here. Try this next one on your own. I know it looks a little bit bigger, but follow that same procedure that I did here, and you should be fine. Alright, pause it and come on back. Alright, welcome back. So I got when t is equal to 6, my function is going to equal to 12. I plugged that 6 in. I ended up getting 12. And hopefully I didn't throw you off. Remember, sometimes we're not going to have these nice, easy numbers to work with. But when h of t, or our y value, is equal to 6, I plugged that in and I solved it, and I ended up getting 9 over 2. Okay, so remember, we solve equations the same way we did before. If you see that parentheses, you got to distribute. Then you got to combine your like terms, get that variable by itself. So if you have a hard time doing this, remember, go back and visit some of my older videos that talk about solving equations. Brush up on that solving equations skill because we're going to be using that throughout this unit. Alright, let's move on to our next example. So we're doing the exact same thing, but here we got two different functions. Up top, let me go ahead and highlight this. I got f of x is equal to 7x plus 4, and then I also have g of x is equal to 2x squared plus 2x. Okay, so a couple things that we need to remember here. If it is in the parentheses, remember, I'm looking for substituting as an x value, right? I got this number in the parentheses. So we got to look at our function name. Which one of these am I going to use, f or g? Well, I got a little f right here, so that means I want to use my f function. So I'm going to take the 7 instead of that x. I'm going to plug in that 6. And then I'm going to add that 4. 7 times 6, 42 plus 4 is going to give me 46. So that means f of 6 is equal to 46. Boom, done. All right. Okay, I'm going to let you do actually, let's do it together. Let's do g of negative 2. So we got to use our g function. So we're going to say 2. Remember, when you substitute, put in parentheses. Sometimes you might need that. 2 times negative 2. So remember, here we want to do orders of ops. orders of operations. Negative 2 squared is the same as negative 2 times negative 2, which is going to be a positive 4. And then we got positive 2 times negative 2. That's going to give me negative 4. And here we got 4 times 2, which is 8. 8 minus 4 is going to give me positive 4. So g of negative 2 is equal to positive 4. All right. Okay, what do we got here? Well, we got both of them. So this is saying, hey, what happens when you plug in a negative 1 into your f function, and then you're going to plug in a positive 4 into your g function. All right, so here we just kind of want to solve both of them. So let's do f real quick. So we got 7 times negative 1 plus 4. 7 times negative 1 is negative 7 plus 4. That's going to give me negative 3. So I need that piece. I'm going to hold on to that, negative 3. Okay, now I want to do the g function. So I got a 4, so I'm going to do a 2. I'm going to put this 4 in here. I'm going to square that, plus 2 times 4. So 4 squared is 16. All right. 2 times 4 is 8. 16 times 2 is 32. And then we get plus 8 is going to equal 40. Okay, so now that I found what f of negative 1 is and g of negative 4 is, they say take f and then subtract g from it. So I'm going to do that here in blue. So I got negative 3, which is my f function, negative 3. I got this minus sign, and then I got this 40 right here. So negative 3 minus 40, that gives me negative 43. And that is how you do it, folks. Okay, so I want you to try these next 3 on your own. Pause the video right here and then come on back. Alright, welcome back. So this one on the far left, it's the same as the last example we did before I left and you guys paused the video. In this case, we were just multiplying them. So we had to find f of 2, 18, find g of 2, 12. Multiply those two together, we get 216. All right, this one in the middle, this is the one that might have confused most of you. Hopefully there's a handful of you guys out there that got it. This is actually a recall of one of our previous units, I believe unit 1, where we talked about multiplying polynomials. So this is my input, r minus 2. So for every x value, I want to put in an r minus 2. Okay, and so that's what I did here. I put this r minus 2, and then we had plus 2 times r minus 2. Now remember, I am squaring r minus 2, the entire thing. This is 2 terms. So this is going to be r minus 2 times r minus 2. And when we have a binomial times a binomial, we got to do that little rainbow multiplying, or if you wanted to draw the box, you could have drew the box. So that's what I did here. I'm setting this up. I already went ahead and distributed this one, all right? 2 times r is positive 2r. 2 times negative 2 is negative 4. Okay, after we multiply this one out, we get r times r squared, minus 2r, minus 2r. Negative 2 times negative 2 is plus 4. This is still on the outside. We drop it down. Went ahead and combined my like terms right there. Okay, negative 2r minus 2r is negative 4r. And then we got this 2 on the outside to get down below. Remember, this still needs to distribute here. And we get 2 times r squared, 2r squared, negative 4r times 2, negative 8r, 4 times 2, positive 8. Last but not least, you got to combine your like terms. Negative 8r plus 2r is negative 6r, and then 8 minus 4 is positive 4. So yeah, it is a lot of work, but if you're solving equations and you're multiplying polynomials, combining like terms, if all of that stuff is good to go, then you are good to go. Remember, if it is not, please go back and visit some of my previous videos. I'm telling you, brushing up on this stuff is going to be very useful because you are going to see this all unit long. All right, and then the last one, it said to solve for x for this the function f, so I set that 25 equal to my 7x plus 4. I just went ahead and solved it, and I ended up with x equals 3. All right, very good. These just take a little bit of practice. That's why I'm going to give you a lot of them to practice with, and you will be good to go. But last but not least, we have an example here. And it says Mr. Martin is selling hoodies in his classroom to raise money for prom. Remember, junior class sponsor here. For each hoodie sold, Mr. Martin will make a profit of $17. I already modeled the function for you. My function is labeled capital M. What is my input? My input for this fundraiser is selling hoodies, and my function is 17x. So it wants you to describe what M of 30 means. So if we look up here, if we know that in my function the H is for hoodies, right, and I'm inputting how many hoodies am I selling, I'm trying to get an output. What's the output that I'm looking for? I am looking for that money, that cash money. Okay, so if I have an input of 30, what does that mean? It's either going to mean $30 or 30 hoodies, as you may have guessed. Yes, so it means Mr. Martin sold 30 hoodies. Remember, that is the input. I am talking about selling hoodies to make money. The money depends on how many hoodies I sell. So our second one, what does M of H equal 170? Well, if we already said the last one was hoodies, then this one is probably, you guessed correct, this means Mr. Martin made a profit of $170. And then last but not least, describe what M of 15 equals 255 in the context of this problem. And I'm sure you've guessed it already because you guys are all fantastically bright. It means if Mr. Martin sold 15 hoodies, how much profit did he make? $255 profit. All right, gang, that is all I have for you. Sorry that it was a little bit of a longer video. There is just a ton of juicy stuff in this unit. Functions are super, super cool. I hope you guys think so. So remember, do the practice. Do every problem. It's very important that you do. Ask for help. Make sure you are actively working. No time for sleep. Let me tell you, get this stuff done. Catch you on the next one. Peace out.